So we're heading into this chapter that is called Dense Correspondence and its Applications. Okay, and so there's actually lots of stuff to cover here. In fact, some of the most kind of exhaustively studied computer vision problems kind of fall into this chapter. For example, problems like optical flow and stereo correspondence, all that stuff is kind of in here. And so, to be honest, you could teach a whole, you could have months and months of lectures on this topic. I'm just going to kind of skate over the key ideas in each of these areas. So we're going to do kind of image registration and kind of scattered data interpolation today, and then we're going to talk about optical flow, which is one of the most important problems in computer vision on Thursday. And so let me first, kind of just specify what I mean. What is dense correspondence? Well, so far, for most of chapter 4, we were talking about features and matching, right? So when we talk about image features, we're typically talking about something where we have, maybe I've gotten a detector and a descriptor and a matching criterion, and I've used those to find, that there are some sparse set of points that match in the image, right? So if you run your SIF descriptor on a pair of images, you'll end up with, a handful of matches, right? And that's what you found, hopefully, in the most recent homework. You ran some, SIF descriptors on your images, and you found some matches. But those matches are not distributed evenly across the whole image, and they're not dense, by which I mean, if I want to know where is the corresponding point of this guy, right, there's no information about where that point is over there. If that point was not one of the original features, I don't really know where it goes over into the second image, right? But there are lots of visual effects applications where we actually have to know where does every pixel in this image appear over here, right? That's what I mean by dense correspondence, is that what we want actually is we want for every pixel to have a little vector attached to it that points over to where that pixel is in image number 2, okay? So kind of mathematically what I mean is that for every pixel, xy, we want to find what I would call a motion vector, which I'm going to call uv, so that if I look at image 1 at the xy position, that corresponds to image 2 at the x plus u, y plus v position. And so a lot of times like I said, I call this a motion vector because the interpretation is that because of either the camera moving or objects in the scene moving or both, that basically the 3D point that corresponds to this location has moved in space relative to the camera, and I want to know what is the vector that captures that motion represented in the 2D image plane, okay? And so there are some pathological cases where motion vector is really the wrong word, right? So for example, there are, if I have if I have a thing I'm holding in my hand and I have a spotlight and I move the spotlight around what I'm holding, all the colors and intensities in that image are going to change, right? But nothing will have actually moved, right? That's kind of one of the pathological problems, is that changes in lighting can definitely cause apparent motion when none physically exists, right? So it can be very difficult to estimate motion, or what does this motion vector mean? In this case, it's kind of hard to define. Another thing that's kind of equally bad is that suppose I have a fixed spotlight and I've got this matte white ball and it's just rotating like a globe here, right? So in that case, if I have like kind of ideal imaging assumptions, all the images I take of this rotating thing are going to look exactly the same, right? So the image will appear to be static, but I know that stuff in the 3D world is moving, right? And so again, that's like a pathological case, right? So generally what we kind of hope for is real world scenes where there's enough texture that as I move the camera and as stuff moves around in the scene, that there really isn't any ambiguity about what the motion vector should be. Okay, so I'm going to kind of ignore these pathological cases, right? We don't really encounter these kinds of perfectly rotating cue balls in the real world very much. And so there are lots of ways to phrase this problem of finding this dense correspondence, okay? And so the one I'm going to talk about today is what I would call something parametric, which means that I can, for every xy in the first image, that this uv, right? So really this u and v are functions of x and y. And a lot of times I'm going to kind of drop this parentheses because it's really cumbersome to keep on carrying around this parentheses xy. But parametric means that these things are, you know, easy functions. For example, an easy function is, say, x plus t1 and y plus t2, right? So that means that to obtain the motion vector field, all I have to do is, for every coordinate xy, I add a vector t1, t2 to it. And that would be what we would call a simple translation, right? And so, you know, parametric what I would call transformations. And so some of these you're probably already familiar with, right? So for example, if I have, let me just kind of draw over here. So if I have xy over here, and I have a corresponding point x prime, y prime over here, so you guys are probably already familiar with some of these guys. So for example, translation is when I have just a simple you know, I take the pixel in one image and I move all those pixels by exactly the same translation vector. Rotation is when I have an angle I guess depending on how you do this, it could be like this. Right, so rotation is going to take the image and rotate it by theta degrees. And of course, if I also wanted to, I could add in kind of a scale, rotation, translation. So if I kind of want to put that together, I could have something like I have a scale factor, and maybe the scale factor is different in the x and y dimensions. And on top of that, I can rotate the image and on top of that, I can add some translation, right? So here, you know, basically that's something like what I would call, this is also called a similarity transformation. And so all these things are parametric, which means that I can specify what happens to every pixel in image 1 just by giving you a handful of numbers. So here, I only have to tell you the 2 translation vector elements. Here I only have to tell you 1 angle, and here I have to tell you the 2 scale factors, the angle, and the translation, right? And then you may have also heard, for example, something called a shear. So a shear is something like this, where I have so this is something, for example, where I could have an image that goes from this to something like this, right? And so MATLAB will happily kind of help you view all these transformations. So for example, so here's an example of an image, and I have a I made a little transformation example. So here I can take the image and I can rotate it by pi over 6. When I do that, you know, I map all the, you know, image coordinates to some new position, and I have a rotated image. And you know, you can keep on doing this with different things. So for example, if I have a shear takes all the pixel values and it kind of shoves it over, like this is what you call a horizontal shear, where everything is kind of pushed over this way. I could have a vertical shear where I'm pushing it the other way. So the main idea is that all the pixels are kind of moving together, right? And they're all characterized by a single small set of numbers. So if I go back to my notes here, so all these things kind of can be subsumed under what's called an affine transformation. So most generally, that's like saying that I have some 2 by 2 matrix here, It multiplies the pixel coordinate, and then I add to it some translation. So here I have 6 parameters. Now, affine transformations are definitely used a lot, especially in image processing. But it's fair to say that they don't actually physically represent what's going on between 2 images taken of the same scene at different times, except under very extremely contrived circumstances. I mean, sometimes you can get away, like if you're standing and you're taking a picture with your digital camera and you're taking pictures of stuff that's really far away, you could probably get away maybe with trying to stitch those images together with an affine transformation, but you'll find in practice that actually you generally need something more than an affine transformation. Often you need what's called a projective transformation. And so a projective transformation is a little bit more complicated. So a projective transformation looks like this. So the way I would write this would be something like so now there's a denominator that wasn't there before. And so here this is kind of like a generalization of an affine transformation in the sense that if I made these C's in the denominator 0, then I would just have a normal affine transformation. Adding this denominator part is what allows me to do some more arbitrary transformations of the image. So a projective transformation can take any original rectangular image and basically put those 4 corners anywhere that I want. And so there's no requirement that what comes out of projective transformation needs to be, a parallelogram anymore. It could just be an arbitrary quadrilateral. And so, for example, here, if I apply just a projective transformation to my image, I could get something that looks more warped, like this. Okay. And it turns out that this is exactly the transformation that you need in several kind of typical scenarios, right? So, for example, if you're standing over a great vista on vacation and you hold your camera and you're taking pictures, where you're really just rotating you're rotating around a fixed axis, right? Where you are the axis. So when you're just purely rotating the camera, then the images turn out to be related to each other by this projective transformation. So when you go into your camera software and stitch these images, what it's really doing is it's finding feature correspondences and it's using them to estimate projective transformations that map those images onto each other. Okay? And so that process is generally called registration. So when you talk about image registration, it basically means putting images together so they're in the same frame of reference. Okay? And so that process now, really, most of the half of it already, which comes from feature matching, right? So the first step in any sort of registration problem is to find corresponding feature points between the pair of images, right? So we already know kind of how to do that. You could use Harris corner matching, you could use SIFT matching, whatever. So now you've got a set of matches, and the next question is, how do you estimate the parameters of the transformation that you need to do, right? And so let's talk about how you would estimate a projective transformation, okay? Well, kind of the easiest way to think about this is, okay, so what I have is, let me just write this over here, to register images with a projective transformation. So what I have is basically a set of correspondences in image 1 and let's call them xi prime, yi prime in image 2. Well, let's look back at my projective transformation equation. So if I kind of pull this back up for a second. So what I'm going to do is I'm going to rewrite these equations by bringing the denominator over to the left-hand side. So I'm going to multiply the left-hand side by this. So what does that mean for the first equation? That says that I have C1 xi prime plus C2 yi xi prime plus xi prime equals A11xi plus A12yi plus B1. And if I do the same thing for the y part, what I get is C1 xi yi prime right, so all I did was I multiplied both of those equations of the previous slide by their denominator, okay? And I think about, okay, so what don't I know, right? I want to estimate the A's and the B's and the C's, right? So I'm going to rearrange this into a linear system. And so let's think about what the rows of this linear system look like. Well, the unknowns are these A's. I don't know these. And I don't know the B's, and I don't know the C's. But I can say, okay, so let's think about this. So I'm going to rewrite this top equation into something that looks like this linear system. So what's multiplying A11 is xi. What's multiplying A12 is yi. Then I have nothing in this equation that involves these guys. I have a 1 that is multiplying B1. Nothing that's multiplying B2. What's multiplying C1? Well, if I bring this over to the left, I have basically negative xi prime, and then I have negative yi xi prime. So that's basically, I took this stuff and I moved it over to here, and what's left on the right-hand side is xi prime. Right? And I can do the same thing for the other equation. Right, so what I did is I put this together into something where I have basically, I have 8 equations. I'm sorry, I have 2 equations in 8 unknowns, right? And so, since I only have to estimate 8 parameters, what I could do is, as long as I had 4 corresponding points, every correspondence gives me 2 more equations, right? And so basically, if I had 4 corresponding points, I would have 8 equations. Then I would have an 8 by 8 matrix equation. I could solve that exactly, right? If I had more corresponding points, which is generally a good idea, then I would have lots more equations than I have unknowns, and I would solve that with a linear least square system like A / B to find the parameters here that did the best job of estimating the original, correspondences, right? So in that case, the estimated transformation is not going to match each of the correspondences exactly, but it will do a good job of distributing the error across all these correspondences. And so this is kind of the most simple idea for estimating a projective transformation. That's not to say there are definitely better ways that you could do it, okay? And so the book goes into some detail on some of the things that you should be doing to make this transformation estimation process better. So one of the things is basically, before you even solve this problem, it's probably a good idea to kind of normalize the points that you use in your estimation problem. And so what I would say is there's usually a step of what I would call pre-normalization, or I guess you just call this normalization. So it could be that initially, maybe my points in image 1 are all over here in one part of the image, and maybe they all have like large values, right? So for example, if I've got a normal sized image, maybe the coordinates of this point are 1,000, 800, right? So in that case, I've got really big numbers that are entering into my estimation problem. So typically what you do is you try and take this cloud of points and you move it over so that this cloud of points is centered at the origin. And you basically should have something like average distance, something like square root of 2. So basically what you do is you take all the points and you kind of move them over to the origin, you make them all have basically the same scale, then you do your estimation problem. Once you've gotten the parameters that you want, then you turn them back into the parameters for the original coordinates by applying kind of a reverse transformation. So basically what I do is, that helps me solve the problem in what I would call a numerically safer way. Otherwise, you may have to deal with really big numbers and really, it's just better to do it this way. So I didn't exactly say it the way I did it in the book, but it's pretty close. This kind of general process is what I would call the direct linear transform. So that's the easiest way to do it. But there are smarter ways to do it in the sense that what we really want to do, if you're a kind of statistically minded person, for example, is you maybe want to get a maximum likelihood estimate, if you know what that means, for the parameters, assuming that you have some sort of model for how noisy the correspondences are. If you want that, this direct linear transform is not going to give you that estimate. But you can do what's called a maximum likelihood estimate by minimizing kind of a different cost function relating these correspondences. The only disadvantage is that then you have to solve some sort of a nonlinear equation. So instead of this kind of a/b that's very easy to do, you actually have to solve something where you're minimizing a function of these parameters that is not linear. And this is not the end of the world. I mean, it's very easy to do this kind of stuff in MATLAB. But it's just to say that if you want better estimates, you have to do something that's a little bit fancier. Okay. The other thing that I didn't really mention here is that typically you also have to do what's called outlier rejection, right? So hopefully, as you saw in this last homework, most of the matches that you would get from some sort of automated program like a SIFT matching program will be pretty reasonable, right? But it could be that you get some sort of oddball matches that are totally incorrect. And those oddball matches are going to throw off your estimation algorithm. And so for that, you need to say, okay, well, how am I going to get rid of these matches that might corrupt my parameter estimation? And one thing that you often see is what's called ransack. So if anyone's ever heard of ransack, I would say this is for outlier rejection. In a very broad sense, what ransack does, it says, okay, for example, if I'm estimating a projective transformation, I need to have 4 matching pairs of points, right? So what I can do is, even if I have 100 correspondences, I can say, okay, over and over again, I'm going to pick out 4 pairs of points, estimate the transformation corresponding to that set of 4 correspondences, see how well that transformation fits the other 96 correspondences, and I keep on kind of drawing these 4 pairs of points until I can be kind of suitably sure that none of those 4 pairs of points have any outliers. So if that's the case, then using this 4-to-4 transformation should give me something that is close to the truth. And so the idea is there's just kind of this probabilistic reasoning about, okay, so if I think that the probability of error is p, then how many times do I need to pick 4 pairs of points out of this set of 100 to be, say, 99% sure that one of those sets is going to be good for me, right? So it's not a very hard analysis to figure out how many sets of points I need to sample in order to get this good estimate. And then ransack helps me identify which of the points that don't match this transformation, then I can just throw those out and then I can re-estimate using all the points, right? So that's the basically high-level, hand-wavy method of doing what I would call registration. And so let me just say that I spent years of my graduate school thesis working on registration problems, so you can say a lot more about image registration. In fact, Dr. Stewart here has this whole company based on image registration, right? His dual line company is basically all about image registration for lots of very tricky images. And so you can also get fancier in terms of, certainly not every pair of images fits together with a projective transformation. So one thing that's not taken into account by that is lens distortion. So you can make a more complicated model by saying, okay, now each of these images has some separate lens distortion, and maybe due to imaging inaccuracies of the camera, things are not exactly related by this projective transformation anyway, so maybe I add a quadratic term or something like that that helps me bend the images a little bit more to my will. And so, there's lots of stuff to say about image registration. So I don't want to say too much about it because it's actually not that common that you have to do image registration problems in visual effects, although it does happen. I mean, I'll show an example towards the end of this whole chunk where, one common thing, I guess I don't have it right on my computer, although I may actually, if you bear with me for 1 second. Yeah. So, hold on. Okay, so this is the same thing. Why is that? Oh, I see. I don't know why this is the image I want here. Right, so if I look at this top image, which I will zoom in on, So what's happening here basically is this is a still from one of the Transformers movies, I think the last Transformers movie, because this is Chicago. And so each of these small things outlined by yellow is kind of the field of view of one HD camera that they're pointing out of a helicopter filming this scene. So basically what they do is they take high-resolution chunks of an environment, and then they register it all together into one big chunk, right? So here, basically, this large panorama has been built out of 20 smaller images that have been registered together, right? So this is one instance where you might want to do registration for a visual effects problem. Okay. So, comments or questions about that? Okay. So what I want to talk about in a little bit more detail, let me just see here. So this is just a picture of changing things. Okay, so I want to talk about in a little more detail something like this, where, the more typical problem, kind of following on from the feature detection stuff that you did in the last chapter is, so I have a bunch of features that I've matched, and here I've kind of numbered them, and I want to think about how I could use those matched features to generate a dense correspondence between the entire pair of image planes, right? You would think that if these images had a bunch of features that matched between them, that I have kind of enough information to imagine what happens in between these features, right? And so this is a problem that I would call scattered data interpolation, okay? And I would use the word scattered because here, in these cases, these features are typically not spread uniformly over the scene in a nice grid pattern, for example. And so you may have heard, if you've ever done any, this comes up in computer graphics, I think, right? Have you heard of bilinear interpolation? So, all the time? Okay, so basically, bilinear interpolation would basically say, okay, so suppose that I have a grid square in image 1 and some corresponding grid square in image 2. How would I know where does this point go over here? Well, what I do is I find these distances, more or less. So it's kind of like saying, okay, if this is A and this is 1 minus A, and this is B and this is 1 minus B, so then I can say that, this point over here is proportionally located at the same position over here, right? So this is very useful when the correspondences between the two images are in this beautiful grid form, right? So I mean, when I have pixels from one image to pixels to the other image, well then life is pretty good, right? But that, as you hopefully saw in the last homework, correspondences in real image processing problems never work out that way, right? So what's more likely is that I have a whole bunch of kind of spread out weird correspondences over here, and then I have a whole bunch of other correspondences over here, and now I need to figure out how do I use these correspondences to estimate what goes on somewhere else, okay? So that's kind of what I mean when I use the word scattered, okay? Meaning unorganized in some sense. So one of the most common ways of doing this is what I would call thin plate spline interpolation, okay? And so again, if you guys are computer graphics people, you've probably heard about splines, B-splines, and so on. And B-splines are one example of the kind of interpolation you can do. So I particularly like thin plate splines because, again, it's one of these things where you can code it up and solve for it in closed form. And this is what I want you to do on the homework. So what does a thin plate spline interpolate mean? So also, just as a side note, so this kind of gets its name from what would happen if I were to take kind of like a piece of metal and I were to fix it at a bunch of known points, and I want to kind of say, okay, well, then what shape does the piece of metal take in between those points, right? It turns out that the shape it takes is what's called this thin plate spline, which is trying to minimize kind of a physical bending energy. So it tries to find kind of like the lowest energy, final position that corresponds to hitting all the points where you've nailed it down, right? And so actually you can find splines and things like, boat building and stuff like that where you're kind of nailing down things in between fixed points. And so the terminology here is a little bit different. So basically this is like saying what I want is a function that takes every pixel in image 1 and produces the corresponding place in image 2. Okay? So, in some sense, if I want to know the motion vector, right, the motion vector here is really like this function minus the original pixel, right? So if I want to kind of bring this back to thinking about motion vectors, I can kind of toggle back and forth between the motion vectors and this function that I want to estimate, okay? So this is really an interpolation problem, right? Interpolation means that I know some points where this function is defined, and I want to figure out how to apply it to any point, right? And so again, a thin plate spline is still parametric in the sense that I have a very particular parametric form. And so let me write this down first, and then I'll talk about what it means. There's a little bit of notation here, unfortunately. Okay, so what do we got here? So basically, first let's talk about this part by itself, right? This part by itself is just an affine transformation, right? So there's an affine transformation, and on top of that I add this other stuff here. So what is this other stuff? So what this is these things, these phis, are called radial basis functions. And so one example of a radial basis function is something like this. And this r is basically the distance from the point I care about to feature point I. So putting this all together, this is like saying, okay, so if I want to know where does an arbitrary point go, what I do is I compute the distance of that arbitrary point to all of the feature points that I actually have matched. Those become these little radii, right? So again, the way I think about this is that if this is point, if these are the points that I've got matched, and then this is my point I care about, then this distance here is R1, and this distance here is R2, and so on. So it's like saying, okay, how far am I away from each of these, originally matched feature points? And then, this phi is a function that turns, this phi is basically a basis function that looks like kind of a bowl around each of these points, right? Because this is kind of like, if I didn't have the log part, this would be just like a quadratic bowl that says the distance increases the further I get away as a square of the radius. And then I have a weight on each of these distances, okay? And so there are lots of parameters in this problem, right? There's the affine parameters, and then basically for every one of the feature points, I have a couple of weights that I'm going to use to try and make my points match up, okay? And so kind of the intuition, right, is that when I plug in a point that is very close to, one of my original feature points, then the interpolant should be very close to the actual xi prime, yi prime that I originally got, and the other weights on the other points that are further away should be lower, right? So that's kind of the way these weights are going to turn out to work. Okay. So I've got basically 2n plus 6 unknowns that I need to estimate, right? So I've got a lot more parameters than I do for a normal affine transformation, but I can still make it work. Okay, so how would I kind of take this parametric form and minimize it, right? Well, kind of the same idea as before. So what I want to do is I want to build a big linear system. What are the things I don't know? Well, the things I don't know are the weights. So I don't know let's see. So basically, I don't know all of these weights. I should have given myself a little more space on the equation here. And then I also don't know what these affine transformations are. I don't know this guy. I don't know this guy. And again, if I kind of think about how is this going to work, well, what's the right-hand side going to be? The right-hand side is going to be basically all of my matches. So I'm going to basically have x1 prime, y1 prime, all the way down to xn prime, yn prime. I'm just going to put little bars like this. This is all going to be 0 down here. And then I think about, okay, so what is this matrix going to look like over here? Well, the matrix over here is going to basically be composed of, well, what's multiplying the affine part is just x, y, and 1. So this side here is pretty easy to figure out. These are just going to be like x1, y1, 1, all the way down to xn, yn, 1. And then what's going to be multiplying all these w's are these phis, right? So going to have basically phi here. Actually, to make this a little bit easier, what I'm going to do is I'm going to just kind of abbreviate these radii like this. So basically this is like saying how far away is point 1 from point n, and so on. So again, we're here. R of ij is basically the distance from these two feature points over here. And then it turns out for symmetry, basically, I'm going to have the same thing going this way. So this is basically going to be a n plus 3 by n plus 3 matrix here, and I'm going to be solving this big linear system. So once I've got this, now I can plug in. So basically, I know all this stuff in all these left-hand and right-hand side, right? This comes from the correspondences, right? All this stuff is built from how the images, how the points are related to each other in the first image, and these are all the points in the second image. Once I've got the weights and the a's, now I can say for any point, I just plug it in and I obtain a new mapping. And so let's look at an example of how this works in real life. So here's an example I put together. So here's image 1, and here's image 2, right? And so for this, what I did was I manually, made a bunch of dots on image 1 and image 2. And you can kind of see that I've chosen these dots in a way that I kind of put them on kind of places like corners and edges where I could, first of all, I could personally vouch for the fact that those were good matches. I don't try and guess where these matches are, like putting them in the middle of empty spaces, right? Now again, you could imagine that you could automatically obtain these matches by using a descriptor matching algorithm, and you could do that, but you'd probably get matches that were much less evenly distributed, right? So for the purposes of this example, I've done it with, kind of handmade matches, okay? Now I estimate my transformation, right? So that means that if I have a grid over here on the original image, I can kind of map, okay, where does each of the grid squares go over in the second image after I map it? And you can see that what I get is basically this, non-linear transformation that is smooshing the intensities from image 1 around over to image 2. So this is not an affine transformation or even a projective transformation because these lines here are all bendy, right? And so that means that, so here is an example of the image that I get after warping, right? Compare this to the original image, right? So this here is basically the pixels of image 1 pushed over to the positions that the warp says they should be at, right? So all the colors in this image come from image 1, okay? And this is the original image 2. And so you can see that geometrically things look great, right? So this is a good registration. You can also see that there are definitely some differences, right? So there are certainly some differences in like shadows and color and so on. It's kind of, if you really dig into it, you can definitely see some differences. So for example, if I go back to the original image 1 and image 2, you can see that like in image 1, I can see like this one back seat showing through, and in image 2 I can see the back seat and then another seat showing through here. So when I look at the warped image 1, you can kind of see that the difference is that, you know, the warped image 1 only has one back seat showing through the window, because that's the only pixel information that ever existed in image 1, whereas the other image actually has the right thing, right? And there's also, like, you know, specular changes, the wheels have gotten in different positions, but for the most part, this would be pretty good, right? And so, you know, this was done basically, this is what I want you to do on the homework, right? So to duplicate this on the homework, first you need to choose a couple of images, you know, either the same object taken from slightly different perspectives is a good example. You have to manually, I think it's probably better to manually do the correspondences between the two images. So for this, there's a MATLAB tool called CP Select, it stands for Control Point Select, that lets you kind of click back and forth between the pairs of images to make it easy to store and generate these correspondences. If you have a, like when I was doing this stuff, I was using a tablet actually, which made life a lot easier, where you can actually have a pen that you're clicking on corresponding points. That will make your life better than just using the mouse. Then you throw those points into your least squares algorithm, the one that you're going to write for the homework. That's going to now produce a, you know, a transformation. Now in the homework, the only thing I'm asking you to do then is to say, okay, you know, choose a point that is somewhere in the middle of this set of, you know, data points that you selected, and then map out where does that point go in the other image, right? So I want you to test a few points in image 1 and see how they look in image 2, if they look reasonable, right? You'll get extra credit if you'd actually take the entire image like I did here and warp it over, right? To do the warping over of the entire image, you have to know a little bit about, you know, interpolation and Delaunay triangulation and stuff like that. So it can be done. Obviously, I did it here, but you have to dig a little bit more deeply into how do you map every XY point in image 1 over to image 2 and then resample the intensities to look good, right? So it can be done. You don't have to do the whole image warping. The main thing I want you to do is to check, do some of the motion vectors that are in the middle of this sea of corresponding points make sense? Question?
Is this transformation, is it usually invertible? So if you found the transformation from I1 to I2,
right?
That was the grid. So when we did this for Chuck's class, we did a homography estimation. When you created the second image, you went from the resulting image back into the first image to pick out a pixel intensity.
Right.
Can you do that here?
So the question is this invertible? What are the other directions? So it is definitely true that if I were to swap the roles of image 2 and image 1, that the two transformations I would get would not be inverses of each other. Okay, so that differs from a homography. So if I were to swap the roles of image 1 and image 2 and estimate the projective transformation, I should get the inverse projective transformation and everything will work out exactly, right? In this case, the order of the images does matter, right? Which is a vote against making it a great algorithm, but I mean, so the invertibility part is a little bit tricky, right? So for example, when you do bilinear interpolation, you're kind of relying on the fact that the transformation is invertible. In this case, it's not, which makes the problem of mapping it a little bit tricky because you have to do forward mapping instead of backward mapping, right? So there is no way, that's a good point. So there is no way to say, okay, where did pixel 30, 50 in image 2 come from in image 1, because it's very difficult to invert this transformation, right? Instead, you have to kind of say, okay, I'm going to push forward all these locations in image 1. So so hand-wave way of doing it, right, is to say, okay, I'm going to take a dense grid in image 1, I'm going to push that grid over to image 2, then I'm going to resample that grid, and then I'm going to do interpolation going back to image 1, right? So basically, you're forced to do forward mapping in this case to figure out what the image should look like. That's a good question, though. Yeah. Okay. Other comments or questions? So this is not the only way that you can do this kind of scatter data interpolation. So certainly, one strike against this algorithm is that to calculate the transformation, or to calculate the function, or even to evaluate the function, you need to know all the image points, right? You need to know all n of those correspondences. And so that function depends on all n of those correspondences all the time. So if I add another correspondence, I have to re-estimate the whole thing, right? So that part is a little bit clunky. So let me just say that the transformation depends on all the correspondences. So that's not great. Better would be something like B-splines, right? So those of you that are, computer graphics people know that B-splines don't have this problem. Right? So B-spline is basically like a local cubic polynomial that I evaluate using, say, like 16 neighbors of a point, right? So that means that if I change some correspondences, then the B-spline doesn't change outside of this local neighborhood. And that makes it a little bit more controllable in the sense that, I don't have to worry about re-estimating things everywhere in the image every time I change 1 or 2 point correspondences, right? And so, B-splines, again, you can do a lot of stuff with B-splines, and so that's another viable alternative for this kind of work. One problem that you can come up with, which is kind of annoying, is depending on how kind of pathological your correspondences are, your algorithm may have a hard time with something like this. So what I mean here is, in this case, this is image 1, this is image 2, so here the black dot is moving left and the white dot is moving right. If I were to estimate a transformation like that, the grid lines of image 1 would get all tangled up when I move them over to image 2, right? There's nothing that enforces the mapping that I get from this thin plate spline interpolation to be the same kind of thing that I could get if I had like a rubber sheet and I was pushing it around on the table, right? What I want to do is enforce that I can't have the sheet fold over on top of itself when I move this stuff around, right? So in mathematical terms, this is what will be called enforcing a diffeomorphism. Diffeomorphism means that I get something that looks like the right-hand side where the original grid kind of smoothly bends to form the new grid, right? I don't want there to be any creases or folds like I have in this image over here, okay? And so again, there are algorithms for doing that. Kind of the easiest way to think about such algorithms is you imagine that the image pixels in image 1 are basically like a fluid that is flowing towards image 2, right? And so you kind of say, okay, my constraints are that after the image is done flowing, all of my correspondences have to match up, and then I put some sort of an energy term that says that the flow can't be too extreme otherwise, right? So it's kind of like saying I want to minimize the bendiness of the flow, subject to the fact that the constraints must be met after the flow is done, right? So that's typically done with a differential equation. And so you can read in the book about how you form that differential equation and how you'd solve it. And so that kind of thing, that kind of thing can come up, for example, in like medical image registration, because certainly in medical images, physically that stuff can't fold over on top of itself, right? You may be able to get away with that in computer graphics, but you can't get away with it inside the human body, right? So that's where some of that stuff was originally done, was to say, okay, if I've got a 3D MRI scan from patient 1, or from a patient on day 1 of treatment to a patient on day 10 of treatment, and I want to know how do I match up their internal organs, well, then you might use this kind of a 3D flow-based registration algorithm. Okay, so just a couple more comments about this idea. So let me just say, can enforce diffeomorphic transformations. Kind of what that means is one-to-one and invertible. Kind of like what I would say, kind of like using a PDE-based kind of fluid flow method. So another thing to know about these transformations, though, is that no matter what you do, it's generally fairly difficult to force what happens between the points that you. So basically, if you have these sparse set of correspondences, it's generally pretty hard to control what happens between those correspondences, right? So for example, using an algorithm like this, there really is no easy way to force a straight line in image 1 to turn into a straight line in image 2, right? There's nothing that makes that true. And you can see from remember the wavy lines in the car image, that typically the image 1 is getting mushed all around to form image 2, right? So you might say, okay, well, something that looked like a nice rectangle over in image 1 could turn into something weird looking in image 2, and there's really not that much you can do about it other than, pathologically add more points that correspond, right? So I mean, at some point you're manually doing the dense correspondence yourself if you come to that level, right? So the other thing that you should be, so let me just say that straight lines generally don't stay straight. Another really, big deal about this is that, the image intensities and colors are not playing a role here. Right? So really, I can estimate this transformation purely based on the geometric XY locations of the correspondences, right? Nowhere in this whole process did the actual colors of the image enter into anything, right? And that seems like a huge oversight, because obviously I should be able to use matching colors in the images to help me drive what the correspondence should look like. I should be using all that information. And so that's exactly what we're going to talk about in the next lecture, is optical flows. Optical flow is basically a way of estimating this flow field. Optical flow is not going to be parametric anymore. So basically now what I'm going to do is I'm going to be estimating these UV vectors for every point in the image, and there's not going to be any sort of parametric consistency to these UV vectors. But on the plus side, I'm going to be using a lot of stuff about the image that I know, right? So that's the idea we're going forwards. What else do I want to say about this? I think that's about all I want to say. So I thought I had some couple more remarks here. Oh yeah, just in general. So like I said, one case where you see this kind of point-to-point correspondence working a lot, if you've done computer vision, is called like active shape models and active appearance models. So if I want to match, for example, a person's face in one image to another person's face, I kind of build these point correspondence models between the corners and the features of a person's face. We're going to come back to that kind of idea when we talk about image morphing after the spring break. So you guys have probably seen I showed you the famous Michael Jackson video, right? So to make that video, we generate a dense correspondence between the images using a particular algorithm for correspondence that involves not feature point correspondences, but kind of line segment to line segment correspondences. So I'll talk about that a little bit after the break. And yes, just in general, what we're talking about here is more generally called deformable image registration, right? So when you talk about image registration kind of without any qualifications, you're really usually talking about something like an affine or a projective transformation, maybe with some sort of lens distortion or something like that thrown in. When you talk about deformable image registration, you're talking about mushing these pixels around in the image in a way that is either non-parametric or requires lots of parameters to describe. And so, again, lots of real-world registration problems are really more like deformable registration problems. But there are some, like for example, taking the pictures on the vacation photos, where you really do use a parametric transformation. And as you can see from the car example, you can usually get away pretty well also with this scatter data interpolation, as long as you've chosen your points pretty well. Okay, so any questions or comments about anything? All right. Well, with that then, I will conclude.